Yes, you can start.
Okay. So, good afternoon, all. Welcome to National Webinar Non-Ferrous Series 4 on study of microstructure and mechanical behavior of aluminium copper alloy for high temperature application, organized by IIF Eastern Region Non-Ferrous Activity Centre. This webinar will be handled by Professor Dr. Sutradhar, jointly his student Dr. Susmita Tripathi. He is also PhD in Mechanical Engineering from Jadavpur University and MTech from NIT Durgapur. I have a short CV of Professor Sutradhar. I will read out in front of the August participation. Professor Dr. Sutradhar, his present position Director of National Institute of Technology, Jamshedpur, and that is equivalent to Central University Vice Chancellor. He has been serving IIF from 2008 to 2023. Still, he is working. He is in the journal section as a editor. And his technical qualification: BE Mechanical Engineering, MTech Mechanical Engineering with specialization in Foundry Technology, PhD in Engineering in 1997. 21 students graduated with PhD degree under the broad area of manufacturing engineering technology, that is metal casting, metal matrix composite, nano composites, metal foam, processing, forging of powder, metallurgical component, aluminium copper alloy development under his supervision. And there is various publication as per Google Scholar, that is 171, citation is 2195, H index is 26, I-10 index is 66. His experience about 22 years and above as professor, above 11 years as faculty member, 5 years in industry. He got various awards. 7 award is there: award for long-standing contribution to IIF Eastern Region on the eve of National Foundry Day 2023. Second, Best Paper Award from Institute of Engineers, India. Best Paper Award from IIF. Eminent Fellowship from Europe Union to work for 1 month at Leuven, Belgium. SERC Visiting Fellowship from DST, New Delhi. Best Teacher in Foundry Technology in Eastern Region by IIF here. Energy Administrator of the Year 2019 by Associates of Energy Engineering US, Kolkata chapter. He also associated with some reputed bodies like the Institute of Engineers as a fellow member, the Institute of Indian Foundrymen as member, Indian Institute of Metal member, Investment Casting of India life member, Powder Metallurgy Society of India life member. He was the convener of a study on technology gap analysis of Howrah Foundry Cluster, sponsored by TIFAC, New Delhi. Reviewed 20 DVDs of 40 hours containing courses on casting design and simulation by Professor B. Robi, IIT Bombay, under Talk to a Teacher project funded by MHRD, New Delhi. Coordinated Fisheries, Food and Spice Cluster of Imphal, sponsored by TIFAC, New Delhi. Also patented some products. 2 patents have been published in Indian Patent Journal, 1 product and process development, 1 patent on stack molding, is under process in German Patent Journal. Thank you, Professor Sutradhar, Dr. Sutradhar. Hand over to you for this session or handle this session. Thank you again.
Thank you very much, Mr. Goutam Datta, for introducing me nicely. Just I want to see the share my PPT. Just give me 2 minutes time. Idhar aa jao na. They have to go to screen share. I think the screen is visible to you, all of you. Hello.
Perfectly okay.
Yes, absolutely okay.
Thank you very much. First of all, I am really thankful to Indian Institute of Foundrymen of Eastern region just to give me a scope of giving a lecture on the non-ferrous casting series 4, number 4. And I am really honored to be here as Dr. Amit Nagji and other people have just requested me. Basically, this is the work of PhD of Dr. Sasmita Tripathi, who has done this work under me at Jadavpur University. I have a small laboratory, particularly in Foundry laboratory in Jadavpur University under Mechanical Engineering Department. And there she has worked nearly for 7 to 8 years, because in between there is a corona was there. And so it took almost 7 years to complete the job. And even what she was targeted, she could not complete in the one side. But other side, I can appreciate her total activity, because she has tried to give other area in the same PhD to more highlight on the microstructural part and correlate with her experiments. And finally, she could do very good international papers. And that's why I thought, among almost 20 plus PhD students, I took this topic because the aluminum alloy, the demand is very, very increasing day by day, not only in automotive sector, but also aerospace industries, due to its excellent castability in the green sand as well as in permanent molding, that's dies and die casting process. And because of excellent fluidity, it is also offers a pressure tightness in the final casting, which is a mandatory for particularly in automotive castings. And therefore, I truly believe that this work, what has been done at Jadavpur University, is really very effective, particularly for those industry who are working on aluminum and its alloys. Now, our area is to see how aluminum copper alloy sustain its property at high temperature applications, particularly automobile. So let me proceed further. I will start from a very basic fundamental, where those who have not any idea how a alloy is normally being nomenclature. So from that I will go slowly. When copper is added, the aluminum copper alloy, how it is designated. When magnesium is added, how it is designated, like this. So now this is the Please see the picture. There is actually 8 groups is there. Where when it is coming 1, 2, 3, 4, 5, 6, 7, 8, that is the cast and it is the alloy, and another is the aluminum alloy rod. Now I will show you. You see, when it is 1 dot 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 dot, at that time it is the normally we are using it is an unalloyed compositions of aluminum only. When 2 is coming, that means it is a copper is the major constituent of the alloy. When 3 is coming, when it is aluminum silicon alloy, 4 is coming, it is alloy for aluminum silicon alloy binary. Then 5 when it is coming, previously 3 was there when it is aluminum silicon alloy with copper. 5 is coming when aluminum alloy containing magnesium as a major element. Like this is nomenclature is there. So it will be up to 8. 8 means this is aluminum alloy containing tin as a major alloying element, like that. So this is the basic structure where a person could understand that what is the major alloying constituent in that particular alloy. Now, during my lecture, I will take 3 abbreviations. That is the solution heat treatment. Normally, we do the non-ferrous, particularly aluminum alloy, which is a very, very responsive in heat treatment. And where normally T6, because this is a little difference from the ferrous heat treatment, and that is called the T6 heat treatment. It is already written in the specific customer specifications that you should follow the T6 heat treatment. That means it is a 3-step heat treatment process. And after that, another one abbreviation which is very important regarding the tightness, or you can say that less porosity or almost absolutely no porosity, tightness of the casting, which is called, which is being very, very important, is for automobile casting, transformer, oil chamber, etc., etc. So in this SDA, secondary dendritic arm spacing. So these are the abbreviations I will use. Now, question is that why aluminum and copper alloy is preferred to other ferrous alloys? See, normally we know that in nickel-based iron alloys or different type of steel alloys where manganese is there. So these are basically preferred for any high temperature applications. Okay, but its density is higher, much higher than aluminum. Aluminum is almost 1/3 in density regarding steel and cast iron. So to get the advantage of you can say lighter alloys, so over the ferrous alloys, aluminum alloys being preferred. So this the case where we have taken only aluminum, copper and its series. We have tried aluminum copper alloy and try to see how it gives the performance at high temperature applications. Now there is a thumb rule is there. Many I cannot say any single person, but it is a thumb rule almost that if you want to make a car or it is automotive or any you can say prime mover, you could make that energy efficient by 25%. And because we can get it if you make it 35% weight reduction. That means if you can make 35% of the weight reduction, then you will can get 25% of the energy saving. But remember that it may be expensive by 10%, but however, for a customer, when a car is customer is getting a car or passenger car, whatever is that, its payback period within lifetime of 10 years is much early. Though apparently it is expensive, but lightweight is, that's why it is preferred to any customer for fuel efficiency. Apart from fuel efficiency, other mechanical parts is also involved. Suppose a light car compared to heavy car, actually light car always that inertia can take very quickly. That means it can start and get its full speed within a fraction of a second. But in case of high vehicle or high weight vehicle, is taking more time to pick up as well as to stop. So lighter weight, apart from fuel efficiency, it is easy to start and easy to move. Number two, now aluminium normally we are alloying with major alloys are copper, magnesium, silicon are the major alloying element. Now the thing is that these copper, magnesium, silicon is only help to increase the tensile behavior of the alloy. Even alloy and magnesium only can give the good mechanical properties under high temperature applications. Now the thing is that it is also observed during our study that most of the aluminum alloys are very, very responsive to the heat treatment. Now, it is another part I am telling you. Now I am talking about always that high temperature. High temperature is what temperature? Normally, from literature, it is observed that around 250, that means 200 to almost 250 to 60 elevated temperature will consider as a boundary condition. That means we will work within the limit zone of 250 degrees centigrade. Number one. Number two, whatever we can make the castings, always our objective is that it should be good castable. If the castability is very poor, that means to make a form of castings in a either sand molding or gravity die molding, gravity die casting, the castability is less, then it cannot fill the cavity. So on the considering the castability, we have to optimize the alloy compositions as well as optimize with the mechanical and metallurgical properties of a component. Now always we think that product will be most cost effective, and that's why if we consider cost effective, then what will happen, that we are thinking for aluminum alloy and optimizing the casting technique, but that casting technique means that castability, and also improve material properties with functional behavior. Functional behavior is very important, whether that aluminum casting is used for manual cover or it is applicable for the automobile engine parts, say cylinder head or cylinder casting, cylinder block castings. So or it's aerospace parts, or it is a aeroplane chair component or that seat components. So where it is basically used. So functional behavior is also very important part. Now if we consider any passenger or normal car, you will see that total engine parts is around 50% of the total weight. Out of that 50%, 90%, that is 40, if it is a 50 kg, say मान लो 50 total car weight is 100, engine parts is 50 kg. Out of that 45 kg, that means 90% from the cast aluminium, and rest 5 kg is from the wrought aluminium, either it is forging part or it is extrusion part. So now maximum 10%. Now chassis is basically around 30% of the total car weight. So if it's a car weight is 100, so chassis must be 30 kg. Out of that, cast alloy is around 27 kg, and last 3 kg is wrought aluminum alloy as mentioned. So body similarly like this. So major car 50% is from the engine part, chassis part is 30, body is 15, and interior decoration is 5%. Now I will come into the next slides where I can say the interior fittings is the 5% is going to increase day by day because of the luxury component of the customers. So this is a picture, just I am showing it, that if 110 kg aluminium you can put in a car, you can replace 300 kg of steel or cast iron. So 300 kg, because it is a 1/3 almost by weight, so you can directly reduce 190 kg of lightning, you can make it lighter. So if 190 kg is basically you can reduce, then you can say at least it will reduce the fuel efficiency as previous calculation. It is around up to 14 to 15% better fuel efficient. Next, this is the chassis part. Just like under you can say car ka jo underbody hai. So there I have made something which is very common and which you can replace by the original iron or steel components to aluminium component. So this could be substituted. You can understand very well what is damping, what is the self-lubricating property, journal bearings are there. So this is basically the parts I am showing, but these components may be pure iron, sorry, alloy aluminum, or it may be composite aluminum. So now it is from the literature I have find out, or my student has find out, that exclusively body parts, auto body, as I mentioned already, because of aluminum is a good formability is also there. Along with the castability, formability is needed for the sheet metal working. And drawing capability is also very good. Now, I want to mention that British Land Rover, which is a V8 engine block, is used. It is used from the aluminum alloys. Now, other parts like wheels, transmission, cylinder heads, and suspensions. Now, this is the thing which is really made from the aluminum alloy only. Now the electric vehicle is taking a very lead in automobile sector. So again, electric vehicle also choosing the main components from the lightweight material like aluminum only. So now our basic objective is this part, or this research work is three parts. First part is the development of alloy system, and it should be preferably without silicon. The silicon which is here, it is only making the wrought aluminum or aluminum copper mustard alloy. So very trace amount of silicon is already in the mustard alloy, but we are not adding any silicon in the mustard alloy. There will be aluminum 50% and copper 50% is the mustard alloy. It is being made by some ancillaries factory in Howrah, and after that we are adding aluminum to dilute copper. Okay, say initially it is 50-50. Now adding aluminum, we make it 3 divisions. I will tell you later on. So with that aluminum alloy, we have made gravity die casting. Particularly, you can say it is not high pressure; it's just gravity die casting. And another is green sand casting. It is our scope of work. Now, after that, after a simple component of step component, which is very easy to analyze the step components for the cooling rate is concerned, from the solidification part is concerned. So we have actually made this aluminum copper alloy from that. After making that component, we made the heat treatment, that is a T6 on the tensile behavior of the developed copper alloy, aluminum copper alloy. And after that, other wear properties also find out. So an effect of solidification also seen in the different parts of a single casting under different manufacturing process, that is either sand casting or die casting. And lastly, she has tried with a simulation software, that is a ZCast software, and that has been basically used for her study. And we have find out the improvement phase for the quality improvement of the castings. Simulation is very, very important, and we have also checked in our laboratory. To check the predictability of the software by adding the lab developed alloy to the database. Now, this software, ZCast software, having some database. Now, with that database, this alloy is also done the validation of this alloy, present alloy, along with the database in that software. So now developing any new alloy, now what is happening? It is from the normal alloy, the process what we are feeling. One is nucleation process. It's happened to any alloy, then crystal growth, then grain structure, effect of additives of aluminum copper alloy are subject to studies. Now, according to scientists, shear assisted processing and extrusions technology can eliminate heat treatment steps. And because normally what happened that some process like extrusion and forging, they are actually do not need any kind of further processing because their process itself taken care of. But casting, it needs some additional primary processes it needs. So again, SHAPE is basically shear assisted processing and extrusion technology. We define the green affordable manufacturing approach that enable broad use of high performance aluminum alloy in the applications of automobile components. Now, what exactly literature says? The literature has so give something, because any PhD student before starting the work, he has to define his or her problem, and that is a literature review. Normally, we researchers find out that almost 25 to 30% time is basically involved in literature review. Otherwise, his or her work will not stand in internationally reputed nahi hoga. So that's why literature review almost, if it is a 6-year project, almost 2 years actually gone to define the problem, which area is untouched or very less number of people have studied. So literature says that aluminum copper alloy gives very good strength at room as well as under high temperature conditions around 150. It is already mentioned. Now heat treatment improve again its strength, its wear characteristics, and also this characterization of cast aluminum copper alloy. We have seen that finally that heat treatment, the solution heat treatment we have done. I will show the graph. We will show the heat treatment curve, and after that we will find out that Al to Cu, which is basically the theta phase of the alloy, actually which is staying in the grain boundary, are basically strengthening or the element, or you can say increasing in the grain boundary, and it is increasing with the copper content. If you increase the copper content, then Al to Cu is coming in the grain boundary and it increases. As it is increases, the total matrix is getting more strengthened. Basically, copper sometimes used as a even grain refiner. Even if sometimes I know that in some steel making, some percentage of copper is giving just for grain refinement. Even I am telling you, the copper in aluminum copper alloy is also one side, it acts as a grain refinement. Aluminum copper content, which is basically it's a aluminum copper, that's why you just see it is 2xx.x series. So here actually literature says the copper in aluminum could be up to 10%, 2 to 10%, but the study gives you more detail that actually it is 10%, but what is the percentage you can get the best suitable mechanical and metallurgical property as well as castable property. Material property is very good, but it is not castable. That means no use of that. So we have find out in our study that what is the percentage of copper in aluminum will be best in castability as well as desired, or you can say optimum mechanical and metallurgical properties. Aluminum alloy containing excess copper, suppose if you give जो moderate जो हो रहा है उसके बाद even if you give, but it could be improved even maintaining copper, you have to add the silicon. But silicon again at high temperature, that means 250 or 150 above, it sometimes behave in a different way. So that is another part of the study. I am not coming into that. Next, addition of the copper with aluminum can impact high temperature operational conditions. So that means that, see, if you want to make the copper in the pure aluminum, that what is that the columnar structure and equiaxial grains, it will result, it is coming different. I will show you when I will see the different amount of copper is coming in the material. So now the recent important elements in silicon. Now what I am talking that what is the effect of silicon in the aluminum matrix. We have already found out that copper, personally aluminum is chosen, as I said, maybe 2 to 10%. Now, in this case, at room temperature and as well as elevated temperature, we will find out that aluminum alloy commonly used are added with copper for improving strength and silicon for better castability. Even the corrosion resistance and as well as the corrosion resistance is also giving, as well as the strength is going at ambient temperature too. But addition of silicon is adversely affect after some point of time. So if it is under some elevated temperature, that is 250 and above, then silicon addition should be restricted after some time. So this work, actually, I will show you that increased copper weight beyond 6% weight with aluminum without addition any of silicon and using the casting as manufacturing by the recent work has been formulated. We already conditioned that we will go little bit about more than 6% of the weight of the copper of aluminum, and without allowing any silicon, how the material will behave, because silicon is not basically recommended for that at least 250 degrees centigrade or above function conditions, temperature conditions. Now I will see that why copper is chosen. Now we have in this present that experiment, we have taken three things, that will minimum weight will make copper addition in aluminum. I have said that master alloy, and you go on adding aluminum and dilute. So assume that we have taken 300 gram or 300 gram or unit of aluminum copper master. Then from that we have taken three divisions, 100, 100, 100. So from 100, one alloy we made with 4% copper. That means we go on adding from 50%. By calculation, we will go on adding slowly with the copper aluminum master alloy, and then we want at 8% and maximum is 12%. So our main focus is 4 to 12% weight of copper in aluminum. So now see what is happening. Now if you see this is the alloy number 1, which we nomenclated as A1. Then alloy 2 is the A2. Alloy 3 is A3. What is the difference? The alloy, I am saying trace amount of silicon. No, that means 0.001 se niche hai. So copper is 4%, aluminum is rest. Alloy 2 is 8 and 92, 12 and 88. Now if you see the copper addition, what is basically affecting on the matrix? Increasing copper content beyond maximum solidity. Solidity limit is motamoti 10%, but we are trying it to 12%. Limit as eutectic temperature aluminum increases the precipitation strength. That means it is basically precipitated and it is strengthened the matrix. And the intermetallic formation is also there, and which can be withstand this intermetallic formation, that is the Al to Cu which is coming out. It is basically trying to help the withstanding a high temperature. On the other hand, increasing of copper content decrease the elongation. That means ductility will decrease. Now the thing is that what are the other parameters? See, we have worked in the green sand environment as well as the green sand casting and gravity die casting. We have changed the variation, and we also studied under different section thickness. So the same casting having different cross sections. So what is the result is coming? So result is the microstructure analysis and the mechanical behavior aluminum copper alloy having copper in the range of 4 to 12% in absence of any absence of silicon are suitable to use for automotive industries, because all industries or engine parts or engine related parts temperature is 150 to 250. So this is the that is a pattern you can understand, and that is a wooden pattern, and that is a dark part of the pattern. Then we have taken from the different alloys. That is A1 alloy, it is coming UTS, then yield stress. The see that 8% alloy is giving maximum UTS and maximum yield stress. Now this is for the again arrangement of gravity die casting. The metal cast iron block of two parts, sprue riser, and then it is see the UTS maximum again. A2 alloy is giving maximum UTS and maximum yield stress. Elongation C, elongation is minimum among the three. So now the copper addition benefits and drawbacks. What is the differences, or you can say challenges? Copper is added to aluminium when the strength is priority. Aluminium, copper are very heat treatable. Aluminium, copper alloy preferred for elevated temperature applications, as is mentioned in our main title. Mechanical properties of aluminum alloy we have tried to see. Castability we have find out. Corrosion resistance and ductility decreases. So this is the spiral mold. You know that this is the very old experiment. We are just putting under different temperature, and the length of the spiral actually shows the castability. So after that, we have made all the points, and then we have taken the heat treatment. This is a very peculiar and very common heat treatment, that the T6 what I have told earlier. So there are one is solution and treatment, that is people are in the industry, they thought is a solution treatment, or somebody says it's a solution treatment, and then it is called the solutionizing. Next it is a quenching, and after that it is aging. So this is the three steps are there. I will show you the graph. So this is the graph where first in the furnace you can this is a room temperature, say 25 degree, and it is going depending on the alloy. So if the basic alloy is say LM11 or LM25, normally it is a 520 to 535 is heating. Then this is the soaking zone. This is a soaking zone. It depends on the thickness of the casting. It may be a minimum 1 hour to 8 hours ho sakta hai. It may be up to 8 hours to 12 hours ho sakta hai. And then immediately falling to the temperature of around room temperature, and then again it is staying for some time, and then again it is heating up to 170, 190, and here this part is called the aging. Basically in aging, it is precipitation hardening also people are saying. So these 6 hours is for, this is for this particular alloy, but even for other alloys, LM25, LM9 or LM11, this may be 8 to 12 hours, and precipitating hardening also it is 3 to 5 hours in case of other alloys. And then after it is, this is the soaking, it is a total hour. So 1 hour, and it is a 1 hour, it is a 1 hour almost, but it is changing depending on the alloy. Now if heat treated, you see the alloys again changes, but this A2 of 8% copper remains, giving the better results compared to other two in after heat treatment also. This is, remember, at that time it was a gravity die casting, and at that time it was gravity die casting, it was 120, 136, 124, elongation is 1. Now after heat treatment, this 136 is coming to 10, and yield stress also improving too much. So properties are improving. This is the gravity die casting and after heat treatment. Now the metallographic properties, because metallurgical and mechanical behavior of any component, basically you have to see that what is the intermetallics presence in the matrix. So this study says that presence of intermetallics are not only improve the mechanical behavior, but also in both the cases it is giving either it is a unheat treated or it is a heat treated. So definitely after heat treatment, this presence of intermetallics actually helping to improve the mechanical behavior. Mechanical properties of alloys are microstructure dependent. Analysis of grain morphology. What is the grain size and whether what is the arm, what is the length? On that, it find out that how the property will be. The presence state analyze the microstructure and its effect. I will show you in the microstructure. See, this is the SDS, that dendritic arm SDS is the high, this is the lowest. If it is lowest, that means it will give a very, very close contacts, or you can say grain structure will be very close, compacted, and it will be, you will get the, you can say that is tightness. So as the tightness is there, so you see property area of is also theta phase. This is the that element, that is Al2Cu. That's percentage in the matrix is 27%. And others cases where the copper is 4%, this dendritic arm structure, the difference is 47, is a bigger size, but area fraction is also less. So this is little again less if it is a 12%. So 8% give the best results. So now alloy A2 is giving the average grain size of 133 and 268 micron, and average grain size for the gravity die casting, green and sand. So this is for green and this is for green sand and this is for die casting. It also noted that die casting, the second phase at grain boundaries are finer and fibrous, whereas the green sand casting, they are coarse and plate-likes. So you know that die casting basically giving very high cooling rate, and so high cooling rate along with the copper, and it gives the very, very fine grains and very compact. So that's why that distance is very less and it is giving very compact. So during solidification after primary phase, which is mainly alpha aluminium, is pushed remaining liquid towards the eutectic composition. Therefore, Al2Cu, this is the eutectic are seen along with the primary phase. Now, the weight percentage of copper exceeds 8%. That means in case of alloy, so exceeds the solubility limits in case of A2 and A3, because that is actually solubility limit 6 to this is 8 and this is for 12. The intermetallics formed in the grain boundaries, these intermetallics of A2, Al2Cu form the second phase responding, improving the mechanical behavior. So if you see this structure, so this is basically a optical microscopy of green cast components before heat treatment. So even you see, this is for 4% copper with the same magnification. This is Al2A3 still more, and this is for the 12%, where the grain boundaries are very, very visible in naked eye. In this magnification 200x, that yes, the Al2C2 amount is going more, and this is basically making the hardness. So this is the for die casting and sand casting composition. You see how this part A1 is more thick. So in that case, grain size is coarse. A2 is little medium, but here see the exception is that again it is going more, it is again more coarser, but at A2 this is in between grain size of the sand cast as well as the same thing, but here in die casting it is giving the best. So this is another one, scanning electron microscope. It is find the gravity die casting, how the things are working under the different. See, it is only 4%, where that theta precipitation in grain boundaries are like this. So when improving 4 to 8, the precipitation of theta phase is increasing, and these are the in between. It is the alpha aluminium, pure aluminium, and then this you take again increasing when the percentage of copper getting 8 to 12%. So this is the again varying with the percentage, same thing in the lower magnification. So this is the, again SDS. You see, this is the lowest, that is the more tightness, and this is the more volume takes place compared to if you go for more copper. So it is visible that it depends on the success things also, because it's the cooling rate also important, as well as the percentage of copper. So if you see this thing, see 4%, this is the elongation. So 4 to 8, it is going to decrease, and again it is going to 12, so it is grain size becoming coarser. So this is the point. Even you see the area, how much it is continuing. So Al to Cu, that grain bound, that is, you see that it is the area is going to increase, but the grain size is going to just in the reverse manner. So now the simulation, what actually we exactly want to do, because we want to ultimately the defect-free casting. So changing the riser dimensions, if anything happened. So my student, Dr. Tripathi, what he has done, the diameter at the base of the riser for the existing caster and mold is 20 millimeter. And in different iteration in virtual process, because we don't have spent many times in the laboratory, it is difficult also. But in simulation, you can do n number of iterations. And in that n number of iterations, the base diameter was modified to 30 millimeter. So it is ultimately came from the simulation. So at that case, when you are taking 30 mm that diameter of the base, no sinkage of the base of the riser after 100% of the solidification. So simulation done for Al to alloy successfully, and which eliminates the sinkage from the riser base. So this is the normal casting situation, where this is the thickest zone, that means last to solidify, and this is the thinnest zone, where, because this is the direction solidification in this arrow. So this is the direction solidification, and this is the part you know that the last. Now after this, if you cross section, that means the cup as a riser, not cup, riser. So riser solidification will be like this. So this is the part last solidify, and it will just shrink like this and to the center of this riser neck. Now this is for the aluminium. It's a real picture. He has taken this is the highest part, little shrinkage with that small 20 millimeter base. But I don't know why she has not given me with the diameter of 30, but there is no shrinkage. So anyway, the aluminium having the copper of 8%, in the absence of silicon, exhibits poor quality of casting components quality, both the green and gravity die. Shrinkage cavities are the best of the riser has been noticed. As compared to the alloy A1, the size and length of the shrinkage cavities are bigger for alloy A2, keeping other factors such as mold temperature, riser size, pouring temperature, and only the increase in copper percentage affected the cast quality. The increase in solution range and the massive formation during solution for the alloy are responsible for the cast. Now, Dr. Tripathi has published 2 papers and 4 book chapters in different places. And finally, I would mention that this work is what she has done, except there are 2 years corona. At the time the college was totally banned almost, so he could not do many parts, but still the novelty of his work and the genuinity of hard work and he has given PhD degree from Jadavpur University, I think 2023 or 24. And definitely, I as a supervisor, I also acknowledge the funding agency, departments of science and technology, New Delhi, for a huge financial support under the Women Scientist Scheme WOSA of sanction number this in 2013, or I think sanction came in almost 2014 beginning, and that's why this work could be completed. So I hope she just called me just few days back that he wanted to do some work, because this work which I wanted to mention in the beginning, that the work means a tensile strength at higher temperature, that means almost 250 degrees centigrade. He should continue with this composition and see how the thing acts at 250 degrees centigrade, the tensile strength and yield stress, how it is behaving, along with typological properties, which I am having the scope in NIT Jamshedpur. So I requested her to come here and complete, and is another one work which may be used as a postgraduate or post doctorate work. So thank you very much for giving me the opportunity from IIF Eastern Region as well as the national non-ferrous community. So I thanks to Dr. Goutam Datta as well as Dr. Amit Nag for giving this opportunity, and my students is also here. If any questions, I will try to answer, or Dr. Sasmita is here, so she can also give the answers. So I am expecting few questions from the audience. Gautam Datta.
Any questions from the participants? You can put forward your queries to Professor Sutradhar or Sasmita Tripathi.
Hello.
Hello.
Hello, sir. Am I audible?
Yes, perfectly.
My name is Tridip Shen. I am in this metal cutting industry for a very long time, and Dr. Amit Nag is also a very close friend of mine. So, unfortunately, this entire industry is dominated by application of ferrous, especially this part of the country. Whereas the other part, they are mostly two-wheeler, four-wheeler. There is a lot of aluminium applications are there. So because of this small size of business in non-ferrous sector, knowledge also is very limited. Whoever is come across this kind of application. Now, my just one question I need to ask you. Like in ferrous, we all know there are forging application. There are two kind of forging. Basically, one is open hammer forging and one is closed die forging. And in aluminium, do we have the similar kind of open hammer forging and closed die forging? Closed die forging, yes, I agree. But do we have also open hammer forging? This is my question.
So, Mr. Tridip, so as per I know,
Yes.
that even in a eastern region, there is a very limited scope. But I have a small foundry aluminium, but I got a just a quotation I got an inquiry from CLW once, and they want basically open die forging, as you are telling.
Okay.
But the thing is that I moved from Kolani to Howrah, many places. They said that this much skill, it is happening. It can do by other methods, by as you are telling open die forging, but very skilled labor is needed. And that much skilled labor, even any industry who are doing forging of aluminium in close, very, very small, say pinions, gears, they're doing. But the component which is around, I can say, at least 5 to 6 kg aluminium, and it is around, I think I can remember, it is around 2 feet long. So this kind of uh, job, they said that we are not that much expert to give the finished product,
Okay.
particularly aluminium. So non-ferrous they are doing, but
Okay.
non-ferrous I have seen closed die they are doing, but in eastern region I have not seen so far the open die forging in aluminium.
But is it a popular way of making some components?
It is it is possible, sir, but the thing is that what I want to mean, open die forging is purely skill based.
Okay.
Closed die is semi-skilled also can work.
Yes.
Because semi-skilled, because the die, closed die, you actually guiding the metal forming.
Right.
Okay,
Yeah.
that's why it is little easier. But
Yeah.
in
Right.
case of open die forging, the metal flow is restriction is very difficult.
Yes.
And that's why I find ultimately I could not coat
Okay. Okay.
aluminium component from railway.
Okay.
I could not.
Okay. Okay.
It
So
may
I
be
can just add on here, Dr. Sutradhar.
only
Here, as you told, that not many ancillary units are here. These automobile ancillary units. So not much of skill there. Now the thing is, steel forgings. Yes, there are lot many steel forgers here, open die and closed die, but it is hard to find any aluminium forgers here. Not many people are doing, and in fact, we have been getting those things from Delhi area. Delhi area, basically Haryana and all other places, there are lot many forging shops. They also do that open die forging as well as closed die forging, and we have been procured lot many forging parts from them. But in Eastern India, I think one or two people are there, one or two companies are there. They do that closed die forging, but not that open die forging. Open die forging temperature control is very, very difficult. So that is the basic reason also.
Okay. Thank you, Amit.
Anyone is there? Any question or queries?
আমরা একটু বলতে পারেন না স্যার
ওদের মিটিং শেষ হয়ে গেছে বাজার যাচ্ছে না
ঠিক আছে
I think there is none to put their queries, and I request Mr. Amit Nag to complete the session with a vote of thanks.
Yeah,
Mr.
I'm Amit Nag, secretary of this group, and on behalf of our entire team members, I wish to render my heartfelt thanks to the audience for their sincere presence and for joining in this webinar. My respectful thanks go to Professor Sutradhar and Dr. Tripathi. Probably Dr. Tripathi, we didn't get more chance for interaction. Maybe next time we'll love to listen from you also.
Thank you.
And it was a really thoughtful presentation of Dr. Sutradhar. I'm indeed grateful to Professor Sutradhar for accepting my invitation to give such a speech on the special non-ferrous based topics. It is also remarkable that he has found time from his busy schedule and has spent such a quality time for us. It was a really wonderful session. Before we wrap up, I must render thanks to entire advisory committee members for their support. Mr. Probal Sen, Mr. Onbushelam, Mr. Goutam Datta, ED Ma'am, Mr. Asutosh Sudu for their guidance and initial thrust to organize such an webinar. And of course, our Alokesh Bhattacharya is there all around performances to make this a successful one. Now, the thing is, I have a small question in the sense that, but before that, I also take this opportunity to invite the audience and other professionals to take the membership of this institute. There are ample of opportunities which the members can enjoy. This is the best platform to get opportunity for networking with Indian foundries and allied industries. Besides that, there are other benefits also. Please contact IIF to know more about these benefits. Now, the thing is basically on the economics part, it is beneficial. This aluminium copper alloy is beneficial to go for this, where energy efficiency is required. But if you compare steel and this particular thing, the weight ratio is around almost 3 times. Now steel we are getting, see, this tensile strength of this aluminium copper is somewhere around 500 MPa, I believe so, 500, 550 MPa. And that is available with 2062 material also is steel. Now steel price is around 60 to 70 rupees a kg, whereas this aluminium copper alloy, we get somewhere around 650 or 700 rupees a kg. So where energy efficiency is required, there will be requiring this type of material. And Dr. Sutradhar has already specified that yes, for energy efficiency, this is most needed. And thank you, Dr. Sutradhar, for giving us this lecture. And we are really happy in the sense we have rather learned lot many things from you. And thanks, Sasmita Tripathi ma'am also.
Thank you,
for
sir.
being here. Maybe next time we'll learn from you as well. Thank you
Thank you,
all.
sir.
Thank you all.
Thank you.
Thank you.
Okay.
Thank you very much. Thanks, everyone.
Thank you.
Thank you, Goutam sir. Thank you, Amit sir. Thank you, doctor.
If you have
Thank you.
anything to say, Dr. Suru?
No. Thanks for all this coordination and taking it up for the level. We'll keep doing this kind of webinars on the regular basis. Okay.
Right.
Thank you so much.
Okay.
Good day.
Okay. Thank you.
Okay. Okay. Thank you. Have a nice